Section 1.4 in honors geometry, we're looking at angles and their measure. First of all, we wanted to define what an angle is. The precise definition is that it is two rays with a common endpoint. Now, that is the technical definition. If I were to have, say, this blue segment and this green segment intersect, right now there are no rays, so it doesn't meet the technical definition of an angle. However, I could turn these into rays and it would have the same result. But this is definitely an angle, even though there's no rays. The reason why we use this definition with rays is because it doesn't matter how long these sides are. For instance, this green segment could go a lot longer, a lot shorter. That doesn't change the angle. So we have an angle here. The way that we name angles is significant. So in this problem, I have 4 different names for this one angle. I could call it angle GHS or angle SHG. I could not call it angle GSH because then it doesn't go in the correct order. I could use one letter. I can name this as angle H. Angle H is what's called the vertex. It's where the point where the two rays come together, and angle H is specific enough. Or I could put a number in there. I could call this one angle 4. As I come over here to the right, I want to talk about this angle that has the double marks on it, this entire angle. So I could call it angle NEW. I could call it angle WEN. But I could not call it angle E right now because it's not specific enough. In fact, there's 3 different angles that all have E as its vertex, so using just one letter in this case would not be specific enough. Likewise, because there's smaller angles inside of the one we're talking about, I don't want to use a number to name that angle. I've mentioned the word vertex. It is the point where the 2 rays intersect. That is one of the ways that we can sometimes name an angle, like I showed in this example on the left. We have an angle addition postulate. So postulates are the rules that don't need to be proved, generally because they're pretty obvious. So what we have here is that the measure of angle FRO, this gray angle, plus the measure of angle ORG, that would be this blue angle. If we add the gray angle and the blue angle together, it makes angle FRG, this entire pink angle. In other words, the 2 smaller angles that are not overlapping with each other add up to the entire angle. Another way we could say this is the measure of angle 1 plus the measure of angle 2 equals the measure of angle FRG. In this case, it's okay to use one number to label those angles. I wouldn't be able to call anything angle R because there are a bunch of angles that have R as their vertex. A little bit with notation here, we put the M in front of it anytime we're talking about the actual physical size of the angle, like the measurement of the angle. Next example, I already have an answer written down. Maybe you want to pause it and try to do this one on your own. I'm trying to ignore what I have here. But using some angle addition postulate, our goal is to find the measurement of angle LEG and angle NEL. So measure of angle AEG is 50 degrees. I have that label with my 3 little marks to mark that angle. GEN is 23 degrees, this one, and the entire angle is 85 degrees. I have that marked off with 1 arc in gray. Now I know that this blue angle plus this orange angle together make up that 50 degrees. This orange angle is already 23, so if 23 plus blue has to be equal to 50, it means that this little angle must be 27 degrees. Likewise, this whole yellow angle, let me try that again. This yellow angle plus this gray angle together have to add up to this entire angle. We're told that the entire angle is 85. We've used up 50 degrees in yellow. So 50 plus gray is 85, which means that this gray part must be 35 degrees. The question is, what is the measurement of angle LEG? LEG, that is this gray angle of 35 degrees. The measurement of angle NEL, so NEL, that would be the orange plus the gray, 23 plus 35, or 58 degrees. A little bit more terminology. I think these are probably words that you're familiar with. The acute angles are the small ones that are less than 90 degrees. The obtuse are the big angles greater than 90 degrees. The right angles are the angles that equal 90 degrees, and a straight angle is a straight line. It's an angle that equals 180 degrees. So those are words and terms you've probably worked with before. The next terminology we have is adjacent, and we use the word adjacent outside of math class. It means basically next to. So two angles are adjacent to each other, not if they're just kind of next to each other, but if they meet the specific definition of two angles that share a common ray, common vertex, but no common interior point. So I have a few examples here that we'll look at and try to decide whether or not they are adjacent. First example is over here. So I have one angle and a second angle. They're both marked, and they sure are right next to each other. And they share this common ray, and highlighted in orange. I know it's only a segment now, but we could just as easily turn it into a ray. So they share that common ray or that common side. Problem is, though, they don't share a common vertex. Here's one vertex, there's the other vertex, so no, these are not going to be adjacent to each other. In our next example, we have the two different angles. They do share a common side or a common ray, which would be this side. However, once again, they don't share a common vertex. One vertex, other vertex, so not going to be adjacent. Next one, I have the yellow angle, which is right over again. So here is our yellow angle. And then the other marked angle is the entire thing in gray. It is all of this. Now, they do have a common vertex. They both have this as the vertex. They have a common side. They both have this side over here. However, they do have some common interior points. What you see in yellow are the interior points of the yellow one. And then the gray is the interior points of the bigger one. And since they have some common interior points, or in other words, since they overlap, that is not adjacent either. Next one to the right, we have all these examples of what is not adjacent. So does this one work? So once again, they have a common vertex, great. They have no common interior points. They don't overlap. However, there is no common side. Here are the sides for one of the angles, and here are the sides for the other angles. They are not anything the same. So once again, not going to be adjacent. Final example, finally we get a smile because they do share a common vertex right there. They do share a common side right here. They don't overlap. They have no common interior points. So this is what adjacent truly looks like. Next example, again, I'd encourage you to switch over to your own notes. Don't look at the answers that I have for any of these problems yet and try these problems on your own. I know I have them worked out right here, but ignore these. See what you can do on your own first, and then come back and check your answers. I'm not going to do any explaining on this one. I'll just give you a chance to look, compare your answers, and look at the work I have to see if you can figure this one out. And that's going to be the same for the next one as well. I'd encourage you to pause the video, try the problems on your own, and when you're ready, come and look at the answer key that's up on the screen. All right, so hopefully you're ready to move on. If not, go back and spend some more time on the previous one. We have our next terminology, which is an angle bisector. It says ray WR bisects angle DWA. That means that the measure of angle DWR, this angle right here, is equal to the measure of angle AWR. That would be this angle right here. Notice that I have the same 3 marks on both of them. That's to indicate that they are equal in size. If, go back here for a second, if this one only had 1 mark on it and this one had 1 mark on it, then yeah, I would say those 2 angles are equal to each other. If this one has a second mark and the other one doesn't, then it's not indicating that they're equal to each other. But in this case, again, we do have the angle bisector, so these 2 angles are equal to each other. Since WR bisects angle DWA, that means that these 2 smaller angles are equal to each other. Even more than that, because these 2 angles are equal to each other and they are adjacent, because they're equal to each other, it means, I'll draw a little arrow going in the other direction, it also means that since this is true, then we have an angle bisector. We'll spend more time on these biconditional or double arrows later. But a quick definition for an angle bisector is a ray that passes through a vertex and splits the angle into 2 equal angles. Next example is down below, so I would encourage you to stop your video at this point and try those examples. When you're ready, go ahead and look on screen and you can see the work and see the answers. And time to start working on your assignment once you are ready.